Hello, family. Thank you very much for hopping on. Today we are evaluating a fascinating problem on circuit analysis from the Northwest Mock. And guess what? There are 10 more episodes to come. And let's check out episode 1 together. It's absolutely bang on. So guys, this is the video this is a problem we're going to be solving and analyzing. It's a very technical problem. I love it very much, but I would really appreciate if you could just pause the video right here and actually attempt to solve the problem yourself before you go ahead and play the video and check out what we have done. Thank you very much for hopping on, and there's a lot of beautiful things to talk about in this particular video and a lot of concepts to break down. Make sure you stick around to the very end. Okay, so to solve the problem, Roman 1 says, calculate the PD between A and B as shown by a high resistance voltmeter placed between the 2 points. Well, this is our circuit. This is point A, this is our point B. So if we put a high resistance voltmeter here, the question is, what does that high resistance voltmeter read? Now, the interesting thing here is you learned in secondary school that all voltmeters have very high resistances and all ammeters have very negligible resistances. And so if the examiner has to be extra precise on this particular property of voltmeters that you already know, that is simply the examiner re-emphasizing that there's a particular assumption you have to make here that this voltmeter is perfect. It's a perfect voltmeter. Okay, that means that it has an infinitely high resistance such that no current is drawn to it. Okay, whenever it has to make this extra emphasis, when you already are conscious that voltmeter should have high resistances, that's what that really means. And so what we can go ahead and do is, all right, now we understand that this already has a very high resistance or infinite resistance. And so how would that affect this circuit? All right, I mean, this is a very technical problem. You have to be very careful how you go about it. So this 12-volt battery is supplying current to this circuit, and so that current comes over here. It has to split into this junction, and then the other part goes to this junction. But now remember that there's a very high resistant voltmeter here, so it has an infinite resistance. What happens to current? Current tends to reject the path with infinite resistance. So this voltmeter is really acting like a multiplier here, right? And so all of the current that comes through the 30 ohm resistor gets dumped into the 50 ohm resistor. None of it goes through that path again, because like there's a high resistant resistor there, an infinitely high resistance to the flow of current, and so all of it goes through this path. So what really happens is this 30 ohm and this 50 ohm begin to behave like they were in series as a result of this voltmeter that is connected here. And this is again all really technical, and you have to be careful. So in any normal circumstance, if you have to calculate the PD between A and B, you would have to travel from A all the way to B like that, right? And that gives you the PD. And so you would have to take into consideration the PD that is dropped across the 10 ohm resistor and the PD that is dropped across the 50 ohm resistor. But here's the kicker, guys. No PD is dropped across the 10 ohm resistor because no current flows through this path. And so effectively the PD that is read between A and B is basically the PD that is dropped across the 50 ohm resistor. This is the key thing here. If you don't understand this, you will not get this problem right. And so to understand that the PD that is dropped between A and B is a PD that is dropped across the 50 ohm resistor, and the 30 ohm and the 50 ohm resistor are behaving like they're in series, that means that this 12 volt voltage would be shared between these two series loads. This is the potential divider rule, right? The potential divider rule simply says that if I have a voltage source like this connected in series to two other circuit loads, then the voltage is shared in a proportion across these two circuit loads such that it respects their resistances. Okay, what does that mean? Let's just go ahead and do it. So VAB, that's the voltage across this guy. Well, okay, this is not really right. Okay, right here I'm trying to first of all get the voltage across the 50 ohm resistor using the potential divider rule. So this AB here is not accurate. Is that okay? So this is V across the 50 ohm resistor. So you take 50 divided by 50 plus 30 multiplied by 12. That's the potential divider rule. Okay, so it's basically just it's ratioed. The voltage that is dropped across any one of the loads, in this particular case a 50 ohm resistor, is ratioed respecting their resistances. Okay, so you see that's a fractional proportion of the entire resistance in the circuit. Okay, perfect. So when I do that, you realize that VAB is simply 7.5 volt. please, that's not VAB, please. That is the voltage across the 50 ohm resistor. But in this particular case, the voltage across the 50 ohm resistor definitely just becomes VAB because no current flows through this guy. So yeah, there was no error. I just really wanted to call it here V50 ohm first, okay, before I could call it. But I think I've already initially explained that VAB in this particular case just becomes a V50 ohm resistor. So there you go. That's VAB, which is just the 50 ohm, the voltage drop across the 50 ohm resistor. Perfect. So we move over to Roman 2 and we have that. What happens now if we connect a 40 ohm resistor here? Then everything changes, because then this path is not infinitely resistive to the flow of current right now, right? So what changes? So let's put our 40 ohm resistor there. And then what are we looking for? We're looking for the PD across AB now. Oh, perfect. This is awesome. This becomes very interesting now. So to get the PD now across AB with a 40 ohm resistor here, here's what we do. Now, I need you to pay attention to a couple of things here. If current leaves this point, gets to the 30 ohm resistor, gets to this junction, of course, the current has to split into this path and this path. Now, the current that is going to split into this path is going to be in series. Well, it's going to render 10 ohm and 40 ohm in series, right? Because the same current is going to flow through them. So since the 10 ohm resistor and the 40 ohm resistors are in series, what that means is I can combine their resistances. So I have 50 ohm here, and then this 50 ohm will directly be in power with this other 50 ohm. So I can now combine the two power resistances there. So what do I get? The power resistances will be, of course, 50 times 50 divided by 50 plus 50. That's how I get the effective resistance for two resistors who are in parallel, right? So you therefore have that the power resistance there is 25 ohms. That makes sense. Now, the good thing here is this 25 ohms will now be in series with this 30 ohms resistor, because I've combined everything here. These two, 50, and then the 50 and the 50 now, they give me 25 ohms. So this is how the circuit now looks like. So you realize that the circuit now ends up again like what? Like a potential divider kind of circuit. So I then have to get the PD that is dropped across this 25 ohms. Remember, I want to get the PD across the 40 ohm resistor, but just follow me here. If I get the PD that is dropped across the 25 ohms, remember that 25 ohms results from every one of these things down here. What do? Well, we apply the potential divider rule. The voltage across the 25 ohm is again 25 divided by the sum of the resistances. We have 30 plus 25, and then you multiply by the voltage available, and that gives you 5.45 volts. That's the voltage across the 25 ohm resistor. But guys, pay attention here. This is the key. This 25 ohm resistor comes as a result of getting the net resistance between these two resistors in parallel, the 50 ohm and the 50 ohm here. Now, whenever two resistors are in parallel, there's a common thing that happens to them. The same voltage is dropped across each one of them. So the voltage that is dropped across this 50 ohm is the same voltage that is dropped across the 50 ohm resistor here. But now I don't want the voltage that is dropped across the entirety of these guys. I want the voltage that is dropped across just the 40 ohm resistor, right? And so what that means is the voltage that is dropped across this 50 ohm, again, which is what? Which is this 5.45 volts. Now, let me make an extra statement. I've just made a statement which you have probably learned in the classroom, that the voltage across this 50 ohm is the same voltage that will be dropped across this 10 plus 40, which is the next 50 ohm here, right? Now, the third statement I'm going to make, which is extra important, is that that same voltage will be dropped across the combination of all the resistances here in this power circuit. So if I combine, so the same voltage drop across the 50, the same voltage that is dropped across the 50 over here, and the same voltage will be dropped across the entirety of the resistors if I combine them. Okay, since they're in parallel, if I combine them, I get 25 ohm. So the voltage that will be dropped across this 25 ohm is the same exact voltage that will be dropped across this 50 ohm, which is the same exact voltage will be dropped across the other 50 ohm here. And so since I understand that this voltage across the 25 is the same voltage here, is the same voltage here, that means that the voltage that is dropped across this 10 ohm and this 40 ohm resistor is simply this 5.45 voltage. So now, since this 10 and 40 are in series, I have to share this 5.45 voltage across them. And I use what? The potential divider rule. Awesome. I hope you got that. If you didn't get that, please reach out through WhatsApp. Our contacts is in the description section of the YouTube of this video. And shoot a message on WhatsApp. We'll talk about the problem, all right? We can even share a call, and then we really try to describe what is happening here. But if you understand it, that's perfect. I love you for it. So now what happens is, if we have to share this voltage between the 10 and the 40 ohm resistor, we use our potential divider rule. What do? The 40 ohm resistor would have 40 divided by 50, because again, that's the sum of the resistance multiplied by the net voltage across them. And so that gives us a voltage of 4.36 volts, and that's your answer to Roman 2. Really technical problems, not West Mocks. That's why we really love them at KC, and we solve them a lot of times because they are really technical. Let's go over to Roman 3. Roman 3 says a current flowing through the 40 ohm resistor. Well, this will be very easy and straight to the point. Why? Because you already know the voltage across the 40 ohm resistor, and you know the resistance of the resistor, so you basically just use like Ohm's law right there. V equals to I arrow, so I is V over R. What does that mean? That means I is equals to, our V there is 4.36, our arrow is 40 ohms, so that gives us a current of 0.109 amperes. But again, always write your answers to two significant figures. So you actually have your answer as 0.11 amperes. Okay, this is the answer that the GCA board would mark, because if you look at the data, the data that is given to you has the data with the least number of significant figures is 1. So you have to make sure that you write your answer in at least one significant figure, or you could actually write it in two significant figures, because the GCE board has a plus or minus 1 tolerance bandwidth. Okay, so you can always, in fact, my general advice I give to all of my students and the KC scholars is that always just write your answer to two significant figures. Always. I'll explain why in the next video. Thank you very much, people. If you liked the video and you understood everything that I talked about in this video, give it a thumbs up. If you have a problem, kindly reach out. If you enjoyed a particular concept, leave it in the comment section below. It would help YouTube to push our content forward and get many more people noticing our work on this YouTube space. Our vision is to get to inspire and impact at least 25,000 young learners across this country, and it would help us greatly if you could share the video and you could recommend our channel to most of your friends and your students if you're a teacher. Thank you very much. Signing out. This is Sir Allen. Bye-bye.
Please don't forget to like, comment, share our videos, and subscribe to our channel.